All right, so for the final official lecture of SPLV 2022, here is Jeremy Zinger from University of Glasgow.
Thanks, Philip. Good morning, everybody. Thanks for being survivors and staying till the end. It's nice to see you all. I want to talk to you about a very practical topic this afternoon. So I'm afraid we're coming out of the world of category theory and the semantics and Greek, and we're going to be very down to earth. Greg Michelson used to divide the Scottish programming languages community into squigglers and bodgers, and we're definitely going to be bodgers for the next hour or so. I hope that's okay. Good. So just to check things are working, I'll ask you a religious question. Hello. Oh, yes, I should better do that, hadn't I? I see that. Got it. Good. Okay, so here is a religious question. Sorry, not supposed to ask you religious questions, are you? But if you don't mind opening up a browser, I'm going to ask you a couple more questions. This is just to sort of warm you up a bit. And go to menti.com and type in the code, and then hopefully we'll be able to find out. Well, from your programming language, you'll be able to infer whether you are a squiggler or a bodger, I suppose. Thanks. So I'll give you a minute to do that, and I might even be able to see how you're getting on. Let me see. Oh yes, very nice, very nice. This is good. Excellent. What was the code? That's a good question. The code is about to appear, I think. Let me see, let me see. I wonder if I can do this here. Whee. Ah, well, that's nice. As a Glaswegian, I feel moderately gratified. Although, as a bodger, maybe I don't. Good, very nice. Thank you, everybody. So I'm going to ask you a few more questions, slightly more on topic later on in the talk. Thanks. Hello. Oh, okay. I will do. Yes, certainly. Presuming these are code markers. Well, it is 7, 0, 2, 6, 1, 5, 2, 8. Thank you. Good. Great. So let's go back to where we were before, which was here, I think. This was my PhD supervisor once upon a time. His name is Martin. Hi, Martin. And Martin invented BCPL back in the late 1960s. BCPL was a systems programming language, probably the first mainstream systems programming language. It's not particularly high level, but BCPL was the forerunner of B, which then at AT&T Labs turned into C, and the rest, as they say, is history. BCPL was a typeless programming language. So when you defined names and associated them with values, you didn't specify anything about the type. In fact, the only type really was the bit pattern. Everything's a bit pattern, effectively. And that bit pattern is interpreted based on the operators that you use with your values. And sadly, I want to try and convince you that this philosophy of typelessness has sadly persisted for the last 4.5 decades. So this is the BCPL manual. It's looking rather faded and jaded around the edges, but here we go. And this in 1970s lingo is Martin Richards talking about his philosophy. Okay, so the language isn't a tyrant that lays down the law. It offers services and is not hemmed in by petty restrictions. And if I could translate this into our language, petty restrictions means a type system. So sadly, BCPL and subsequent systems programming languages that followed that philosophy don't really worry too much about types. And really, of course, this is what happens at the low level in the assembler or machine code that's executing on our systems. So this is an excerpt from the ARM developer manual for a memory access instruction, a load or a store. So it says the base register must always be an X register. That's a register that holds 64 bits. You can also have 32-bit offsets from these 64 bits. The X registers store integers and addresses. So again, we have this continued conflation between bit patterns that represent integers and bit patterns that represent addresses in memory, pointers. Okay, so here are some variants of the ARM assembler mnemonic. This is load here, and you can load directly from an address that's held in a register, which is just an integer register, or you can offset from it or indirect through a second register or do some shifting as well. But basically, everything comes via these bit patterns, which are just integers in registers. Okay, so let's think about C now. We're becoming slightly more modern. Instead of the 1960s, we're now in, well, the 1990s. This is the ISO C standard here, which says an integer may be converted to any pointer type. Oh dear. So I shall now demonstrate this just to show you that we are still living with the legacy of Martin Richards' typelessness. Can I do that? I think so. Okay, so here's my program, right? Okay, and I can just say something like this. I can say int x equals ox a b c d e f. Okay, and then I can say int star p, oops, p equals int star x. And that's all absolutely fine. And then if I wanted to, I could probably return star p. This is going to compile. I don't think it's going to run, but it's certainly going to compile. Good. Okay, so I get a warning. LLVM have given me a warning. I think this is LLVM on my Apple machine. Okay, it says you're casting from casting to an int pointer from a smaller integer. So on my 64-bit machine, my ints are probably 32 bits, and my int stars, my pointers are probably 64 bits. So I do get a warning, which is okay. But if I were to do this and just turn this into a here we go, a long. Oh dear, then I think even my warning goes away then. Let me see. Oh yes, look, it's just compiled very happily and everything's happy. I can run it now and I will probably get a seg fault, which is good because I just sort of manufactured a pointer out of nowhere, out of thin air, and then tried to dereference it, and my memory protection isn't going to let me get away with that. Okay, so that's demonstrating that I can sort of synthesize pointers into memory from integers. Okay. In that particular case, I got a segmentation fault because the address that I was trying to access wasn't mapped in memory. So this would have been an address on an unmapped page. So in my page table, when I tried to look this thing up, it would say, oh no, you don't have permissions to access that. And so I get my segmentation faults. But if I could manufacture a pointer that did point to something that really was mapped and was accessible, then I could actually dereference that and get things out. So I think this is what my next demo shows, into pointer.c. Let me see if I can do that one. This is one I prepared earlier. Let me see. Int to pointer.c. So let me see. Dear. No, that doesn't look right, does it? I think I need a different one, maybe. Let me try this one here. Fake pointer.c. Right, okay. So I've got my integer I. Okay. And now P is going to take the address of I. I is a variable that lives on the stack. So P is now pointing to that address on the stack. And then I can print the hexadecimal address that is P. Okay. I'm casting the pointer to an integer, then printing its address. And then I can print the thing it points to, which should be I, so that should be 0. And then I say enter a value for I. And I'm going to receive that value and read it in as a hexadecimal value. And then, oh dear, I'm going to cast Q to that value. And then I'm going to read from Q. So what this lets me do is look at an address that really is mapped and then manufacture a different address that's going to be fairly close to it, hopefully. Let's see if this works. What was it called? Fake pointer.c. Okay, good. So now I'm going to run it. Okay, so there we go. So the address of my value that's on the stack is 7FEE87 blah, blah, blah. It's a big address because this is a 64-bit value, and the value that's stored there is 0 at the moment. So if I were just to copy that value, okay, then that value is going to be read into the variable I, and then I'm going to dereference it through a new manufactured pointer. And this is the pointer value, and this is the thing that's in the pointer value. That's fine. Okay, but what if I were to go to a slightly different pointer value? Now you'll notice, look at this. This time the address is different. And this is because every time I run my executable, the operating system is slightly randomizing the address space. So things aren't always in exactly the same place, which means that you can't sort of ahead of time determine where things ought to be. This is address space layout randomization, but I know what I is. So let me look a little bit higher up the stack, perhaps. Oh no, higher up the stack will be going up, won't it? 40. Let me see what's there. Ooh, now this is very interesting. I've gone up higher up the stack, okay, and the value there is pointing to something higher up the stack. This is perhaps a frame pointer pointing higher up the stack, you see. And so in this way, you can exploit the system. Well, this isn't a good exploit, really, is having to type in the address, but you can exploit the system by reading stack frames that you shouldn't be able to access directly. Okay. So what we've discovered is, in C at least, our pointers and our integers are interchangeable. We can convert between pointers and integers quite happily, and this is allowed in the ISO C standard. We might get implementation defined behavior, or sometimes we might even get undefined behavior. But if we know what our compiler does and what operating system we're running on, we can often anticipate what ought to happen. Okay, so let me enumerate 3 problems with pointers. What I want to do is to try and motivate the need for more sophisticated ways to access memory, which is going to move us on to this notion of capabilities. So 3 problems with pointers, and perhaps you're already aware of these 3 problems. Maybe you don't even encounter these 3 problems in your high-level programming languages, but the problems are definitely there. So as we've already seen, it's very easy to manufacture pointers out of thin air, or at least out of integer values, out of bit patterns that we could construct either directly in the source code or dynamically through some kind of pointer arithmetic or something like that. Okay, so this int star cast here is manufacturing a pointer, synthesizing a pointer. Okay. The second problem is that our pointers in unsafe languages like C aren't bounded. So I can define an array here to be 10 elements long, and then I can read past the end of the array, perhaps read before the beginning of the array if I want to. And you've seen this kind of behavior in C programs, I'm sure. So here's another example. Oh, look, so here's my secret password. And here's my username. Okay, and I'm going to put my password in there and my username in there. And then I'm just going to iterate over successive byte addresses from the start of the user string. And I'm going to go for 30 bytes rather than the 10 I ought to be going for. And I'll read off the end of the first string and get onto the second string, I think. Let's see. Oh dear. No. Yes, so I read past the first string and then I read past the second string and carry on reading a bit more junk, but you can see that I've been able to access one string from another because they're close to each other in memory. So we have these kind of bounds problems. Pointers don't have bounds associated with them directly, and so we can read off the end of pointers. And we can use stale pointers as well. So if we're dynamically requesting memory from our memory allocator with malloc or something like that, and then we free memory, we say, I'm not going to use pointer P anymore. Well, we are saying we're not going to use pointer P, but we still have the value of P there. And if we do use P in the future, there's nothing to prevent us from accessing that memory, which we had said we weren't going to use and possibly is being recycled, is being used by somebody else, which can cause all kinds of corruption and so on. Okay, so these three problems here are common pointer problems. The first problem is provenance. This is manufacturing pointers out of thin air, this pointer synthesis. We can sort of create pointers that haven't really come from anywhere genuine. The second problem is spatial safety. We can go out of bounds from our pointer, which is only supposed to access a restricted portion of memory. We can move beyond that memory and access memory nearby, as long as it's mapped. And then the third problem is to do with a temporal safety. We could reuse pointers that should no longer be valid because we've freed them. So we can use stale pointers. Okay, so I want you to think about solutions to these problems. And what solution would you propose? So I think, oh, hang on, I might need to do something clever here. You might be able to, let me see. Yes, you might be able to vote on whether you'd rather use a type safe language that would presumably prevent these kinds of horrible pointer manipulations. Run your code with Valgrind or Memcheck, or use some kind of clever allocator that has red zones or address sanitization that might prevent you from doing anything dodgy. Okay, oh, the people have spoken. This is very exciting. Now, can I show you what they've said? Possibly. Maybe not. Do I need to do something clever here? Ah, good. So as expert squigglers, you're all preferring to use a type-safe language. That's fine. Okay, okay. Some people would like to run the thing through a dynamic a checker of some kind to see. Oh, and we've got one. Thank you. Thank you, whoever voted for address sanitization. That's nice. Okay. Yes, if this were the Conservative Party, then the Rishi Sunak solution up here is the one that you're going for. Good for you. Well, the problem is, of course, that sadly, well, some people are using Rust and so on, but even in that language, which is has a more sophisticated type system and is used for low-level systems programming, you can still kind of do unsafe things in unsafe blocks and so on. So type safety does prevent some of these problems, but when you're writing your device driver and so on, it perhaps still has some corners that you can't get round. Using Valgrind is a good solution, but it's going to slow you down an awful lot. Maybe your code's going to run 20 times slower, but maybe just run it in Valgrind once to check that things doing what you want it to do and you're not kind of reading any dodgy values from initialized memory and so on, and then you kind of deploy it after that. And then the address sanitization of the red zone, this sort of allocates memory, leaves huge holes. Now you try and access memory in the holes, then there's some kind of instrumentation to say, oi, you shouldn't be accessing this out of bounds value here. So there's a memory inefficiency and then runtime overhead from the checking for all these things. So is there a better solution? Is there a better way to avoid problems with our pointers? And I'm going to tell you about how capabilities might solve our problem. Good. So first of all, I want to tell you what a capability is, and then I want to talk to you about CHERI, which is a particular instantiation of the capability concept. Okay, good. So just to get a measure of the audience, this is the last piece of audience participation for a while, I promise. I wonder if we could just answer this question here. So, this is just asking you about your background in terms of CHERI capabilities. Good. Okay. So there's a few people in the audience who know about it. Great. You can ask them all the difficult questions. There's lots of people who don't. And I'm hoping they want to. And there's some people who do want to know more as well. That's fine. Okay, great. Right. I'm going to close that down now. I think that's the end of our Menti participation. Thank you very much. That was to stop you all falling asleep. Right, so let's think about capabilities. And here's my kind of definition. A capability is an unforgeable token of authority that grants rights to perform an action in an execution context. So the idea is with a capability is that you have been granted permission to do something, and that permission has been granted to you by a higher power or a more privileged person than yourself. And then while you hold that token, you can do the action, but that token may be revoked by the higher power, or you may choose to pass on that token or some portion of that token to a child process, somebody who is going to do things on your behalf. Now, I'm a bit worried that I might have lost my Zoom screen there. Am I still sharing on Zoom? Well, it says I am sharing. That's okay. Good. The little Zoom tab disappeared. Hopefully it's still appearing. Okay, so here's my trivial analogy. Okay, so a pointer is a bit like a kind of access all areas badge. Okay, so you can go anywhere and do anything with your pointer. Okay, whereas if you are trying to restrict things in terms of spatial safety, then you might say, well, you're only allowed to go to a particular place. Okay, so you are allowed to sit in a particular position, say, or you're only allowed to, this is temporal safety now, only allowed to access the facility at a particular time. Or more commonly, both things, you can be in a particular place at a particular time and only there and only then. Okay. And capabilities allow us to enforce these spatial and temporal restrictions on our memory accesses. Here's another example, an example that's perhaps a little bit more familiar to us and more kind of close to our domain of expertise. So really a file handle is a capability. It allows us to operate on a particular file with a particular set of permissions. So here I'm allowed to read from this file, but if I'd specified W, I might be allowed to write to the file. So hardware capabilities have been around for a long time. If you walk into the computer lab at Cambridge and turn left and look down this sort of big corridor, the street, at the end is, I think it's still there, the CAP computer. And this is a 1970s hardware instantiation of capabilities. So each process could only access particular units of memory based on the capabilities it was assigned. And more recently, in the last, probably over the last decade, folks at Cambridge have been thinking about capabilities in a more modern context. So this project here is pronounced custard. Custard, there we go. Which, does it say what it stands for? Oh dear, no it doesn't, but never mind. It's the brainchild of Professor Robert Watson at Cambridge, who's worked with a lot of other people to instantiate this thing called CHERI. So CHERI is capability hardware enhanced RISC instructions. The idea is you've got your RISC instruction set, whether it's ARM or RISC-V or MIPS or whatever, and you can sort of bolt on an extension to that processor architecture, that instruction set and the processor design that allows you to support capabilities natively in the hardware. And the UK government bunged ARM millions of pounds to actually build one of these things. So you can request to get from ARM a Morello machine, which is actually a CHERI enhanced version of the ARM architecture. This has extra instructions and extra lines in the data bus and so on to support capabilities. So we've got 3 of these machines at Cambridge. I think there's a couple that, sorry, we've got them at Glasgow. They've got lots of Cambridge, of course. And then there's a couple at Edinburgh as well, I think. And, oh, yes, that was nodding good. And they're kind of available on request from UKRI, if you ask them nicely. This is all part of the Digital Security by Design initiative, which is a large funded project from the UK government. Okay, so just returning to our notion of capabilities, let's try and think about what this means in the context of memory. Okay, so we're going to say that capabilities are unforgeable pointers, okay, that grant us rights to access memory in a particular execution context. Okay, so because it's unforgeable, that means we can't kind of synthesize pointers out of raw bit patterns. And because we're only given particular rights, that means we are restricting the operations that we can perform, whether that's, you know, RWX or maybe something else that we can do in a particular process with a particular value. So we're used to pointers ever since, you know, BCPL days. We're used to pointers just being word length bit patterns that we can use to address an area of memory. But suddenly, pointers, now called capabilities, have acquired a lot more information. They're much fatter. Fat pointers, the technical term. So now our pointer needs a base address, okay, and it needs a limit, and then our pointer to be legal must be anywhere between the base and the limit. I think including the base, but not including the limit. Okay. We can have out of bounds pointers. So really the base, the pointer and the limit can all be full 64-bit addresses in a 64-bit address space. And then we have metadata that encodes things like the permissions, what we're allowed to do when we use this pointer, some kind of type field as well, which is used for encoding objects and operations and objects, and also whether the capability is sealed, which means whether we can actually use it or not. And as well as that, there's this extra bit here, a tag bit. And this bit is set to 1 when the capability is valid, and set to 0 when the capability is invalid. So we'll think about what that means as we consider the microarchitectural implications. Okay, and the take-home message from this side is supporting capabilities can be expensive. Well, you can see that, can't you? Where previously you had a word length value for a pointer, now suddenly you've got, well, possibly a 3.5 word length value for each pointer out. That's going to affect your cache, certainly. It's going to affect the registers, which have to be wider. And then maintaining these tags for validity is also going to affect the logic inside your processor. So the idea is, if I fiddle with this capability, the bit value in an illegal way, then the tag bit silently gets set to 0, which means then the capability is invalid and can't be used. You can only dereference a capability if the tag bit's set to 1, so it's a valid capability. And then if the pointer is in bounds, you know, greater than or equal to the base and less than the limit. Oh, and also if the operation you're doing respects the permissions that you have in the metadata. So there are 3 checks there. Okay, is it a valid capability? Is it an inbounds capability? And are you doing something you're allowed to? Okay, so there's lots of dynamic checking, and then exceptions if those checks aren't satisfied. There are implications. Oh, a question. Thank you. Yes.
I do other things to check the range of the pointer, like how many processes more limit the number of accesses.
So you're talking about who owns the pointer, perhaps?
Yes. So can I express that? Those kinds of things.
Yes. So with a higher level encoding, you could have some notion of ownership, and that could be encoded in the metadata, perhaps. But I think directly in terms of raw instruction set support, that's not available. So it would require a higher level runtime to support some notion of ownership, I think. Yeah, thanks. Can you do a checksum? Let's go back. Go on. Yeah. Okay. So if somebody were to modify, say, the base or the limit. Right, okay. So the way to do that would be to write to this bit pattern in memory. But as soon as you do that kind of write, your tag bit flips from 1 to 0. So your pointer becomes invalid. You can't then use it to dereference. Yes, good. So there's a sort of root of trust here. Yes, you're talking about where do you get the original kind of valid capability from. So when your processor gets turned on and your operating system boots, your operating system has a sort of a super capability, the kind of a root capability that can access anywhere and do anything. And then as further processors are initialized by the operating system, they get more and more restricted capabilities. Okay, and you have this idea of monotonicity. So a child process can only do less than a parent process, and you can never kind of upgrade your capability permissions to. So you're asking, how is this monotonicity enforced?
Yeah, like that. Like, if you just like privileges with bitwise name, kind of like you have these are the ones you have, so what your parents have, what we do with that.
Yeah, so you can't upgrade capabilities because to try and upgrade your capabilities would involve writing into the metadata. And as soon as you write into the metadata, then your tag flips to 0. Basically, anything you try and fiddle here, apart from changing the pointer, is going to flip your valid tag from 1 to 0. But if you're a parent process, something higher up the trust chain that has the capability to write to this area of memory, then you can use capability instructions to modify the base and the limit, but only if you've got the privileges to do that. So basically, you've got this kind of cascading trust tree, I suppose, where high up you can do lots and low down you can do less. Yeah. What happens at the beginning? Yeah. Okay. So I think there are two main operating systems that have been ported to this this architecture. There's BSD, CHERI BSD, and Android Linux. And I think I'm right in saying the Android Linux uses sort of trusted execution environment primitives to make sure it all works properly. I don't know what the CHERI BSD does. We should check that and see. So if you could intercept the thing right at the start and sort of grab that God capability, then yeah, you'd be able to do anything effectively. Yeah. Okay, thank you. Another question or a comment, please? Yes.
So yeah, I also have a question on the tag bit. So is it the operating system that can change tags?
Good. Let's talk about tags. That's really important. Yeah. So the color data fields here, apart from the tag on the left, those data fields there are sort of in memory. Actually, they don't occupy 256 bits. They only occupy 128. They're slightly compressed. We'll talk about that later. So there's 128 bits in memory that store these fields here. Okay, the tag bit is out of band, so that's the 129th bit, and that is stored in a separate bit vector in your DRAM, or a separate bit value in your cache lines, or an extra 129th bit in your registers, and it's not programmer addressable, so you don't have access to this tag. You can't modify it at all. It's only modified directly by the processor as a side effect of other instructions being executed. Yeah, thanks. Hello, yes, please.
Yeah, so what if I want child to modify some part of the metadata? Can I get like?
Can the child modify some parts of its metadata? Yes, so you can modify your metadata, but you can only downgrade permissions. You can't upgrade permissions. So you could, your child could restrict itself more than you told it to, but it couldn't unrestrict itself.
Can you make a copy of the pointer?
Yes. Can you make a copy of the pointer? Yes. So it is possible to memcopy these things, and the tags will be preserved in that sense. Yeah.
When I enter like a critical section, take a copy and downgrade myself, and then kind of.
Yes, that's right. So you could take a copy of a capability, downgrade its permissions, and then as long as you retain the original capability, you can then upgrade back to that original privilege level. Yes, thank you. That's good. Was there another question? Or not?
So it's like it forces the user distinction by hardware.
Right. So you're talking about the difference between kind of user mode and kernel mode. Yeah. Effectively, this allows us a much more fine-grained set of privilege levels or sandboxes, effectively. Yeah. So instead of just having these sort of two different domains, you now have a whole range of fine-grained protection domains in some sense.
Which is why the operator rating system also use capabilities to enforce.
Right. So you're asking, does the operating system need to be capability aware? And the answer is very definitely yes. Yes. So this requires massive software porting efforts, which is why lots of money is being sunk into this project to pay software developers lots of money to port systems code. So we'll see later on that sort of user applications don't really require many changes, if any at all. It's more the sort of systems level code that does require modification to become capability aware. Yeah. Okay. So my favorite trick is, do you know, you can have a linked list, a doubly linked list with forwards and backwards pointers. Have you seen this? Where the forwards and backwards pointers are XORed into a single word. And then you can sort of XOR them out to get back the forward and backward pointer and then to move forwards or backwards. So that's rather disgusting. That kind of code is not capability safe. There was another question somewhere. Ah, hello, thank you. This is very good. I'm liking all these questions. Please shout it out.
Sure. So maybe you'll talk about it later, but if you could mem copy these.
Right. If you can mem copy these values, yeah.
Are there separate tags associated with all of them? And if so, how?
Yeah, okay. So basically, every aligned 128-bit segment of memory has its own validity bit. So there's a massive bit vector somewhere with 1 bit for every 128 bits of memory. Yeah, so capabilities must be stored in aligned units of memory, and there's a tag associated with that. Thanks. Yeah, hello. A hardware permission. Yeah, okay. So I think why are we using the word capability? I think some of this is for historical reasons. You know, capability-based systems have been around since the 1970s. And I think this is perhaps just the sort of latest instantiation in that long sort of genealogy of research. Yeah, okay, thanks. But effectively, you're right, these are pointers with permissions. Yeah, that's right. Good. Oh, question at the back. Sorry, shout it out, please.
That's a little question. Can you also put usable capabilities?
Ah, good. The question is, can we have user mode permissions capabilities? So you effectively want to use some of the bits to indicate your own sort of application specific metadata. Is that what you're saying? Okay. So there are spare bits, there are unused bits. And could you use them? I think the answer is yes. I think so, but we need to check that and see. Yes, there certainly are bits there to be used. You'd probably need runtime support to encode your permissions, but yeah, I think that might be possible. Yeah, good. Okay, I'm going to press on here because what time's lunch? 12:30. 12:30. Okay, cool. Right, so let's think about systems programming implications. So pretend you're C programmers for the moment, and you've always assumed that the size of an integer, or the size of a long, was equivalent to the size of a pointer to, well, void star, really, I suppose. And now they're not. Now our pointers are all fact pointers, 128 bits, as we'll see later, and our integers are still languishing at 64 bits or maybe 32 bits. And you wanted to cast between your integer and your pointer. You now lose information if you did that. You can't do this arbitrary casting. And you want to make sure that your pointer is now going to be in bounds and have the tag bit set and the valid permissions before you actually do the accesses. Otherwise, something terrible happens, as we'll see later. So, coming back to the problems with pointers, which we thought about before, we had these three problems, didn't we? Provenance, spatial safety, and temporal safety. Provenance is now handled via the tag bit, this metadata, which kind of comes down to us from on high, that tells us that our pointer is valid. Okay, and we can't manufacture pointers, we can't synthesize pointers from bit patterns because you can't synthesize a tag bit. Okay, that's something that's not in your remit. Spatial safety is now possible because although you can have out-of-bounds pointers, you can't dereference them, because when you try to dereference the out-of-bounds pointer, a hardware check takes place and you trap. Okay, temporal safety. Ooh, so this is a bit more tricky here. This requires some kind of runtime support to revoke pointers, perhaps just to turn a tag bit to 0 once a pointer has been freed. The problem is, of course, if you say free P, well, you can go and unset that tag bit, but there might be other copies of P. So what you really need to do is sort of quarantine P, and then at some later point go and sweep through memory and look for copies of P, a bit like a garbage collector would do, and then unset all the tags associated with those. Oh, this is interesting. I think I can plug in my charger here. Oops. Good. Okay, so it is possible to avoid staleness. Right, so I make it half time. I was going to start with questions, but we've had lots of questions already. And well, let's stop for a couple of minutes just to have a natural break, and we'll start again perhaps in 5 minutes. Thanks. Oh, that's clever. Okay, good. Hello again, everybody. Thank you for coming back. Let's carry on. So in this second half of the talk, I want to get to the stage where we build our own memory allocator on top of the CHERI platform. So just a quick recap. We've been thinking about fact pointers. This is a diagram from one of the original CHERI papers. So we've got a base, which is 64 bits, a limit, which is 64 bits, and then an address, which is 64 bits. And the point is, the address can be outside of the base and the limit. So that's why we need the full 64 bits there. Then we have this sort of permissions, metadata, and some kind of object type metadata as well, and some unused bits. But overall, the fact pointer fits into 4 words or 256 bits of memory. Okay, so we should have a look and see what happens when you go out of bounds. So let's write a very simple program to do this, and hopefully I can. Let's see. Ooh. Right, so this machine here has the CHERI compiler on it. It's just a CLAN compiler, and I need to give it the right flags, which I carefully saved somewhere else. Okay, so we can write code now that's hopefully going to compile. This is a cross compiler, and then we should be able to run it on our own CHERI machine. So, oh, there's already a test.c, that's useful. Okay, so right, so let's allocate some memory. Int star p equals int star malloc. Let's say 5 star size of int. Will that work? Hopefully. Okay, so I've got a buffer that can store 5 integers in it. Okay. And then we're going to say for I equals 0, I less than 5, I plus plus. And then we're going to store p I equals I. And then should we just printf pi as well, maybe? Okay, great. And then we'll return 0. So this program should work happily. Okay, now I'm going to copy that to my Morello machine. Okay. Oh, that might not work. Let me try that first. Good. So how exciting. So this is actually the ARM Morello machine. Look, this is our real kind of bit of silicon that's actually running CHERI BSD in Glasgow. And if I run my program, there we go, I get out 0, 1, 2, 3, 4, because I just iterated over the values in the array as it was. But if I were to change the program, so I went out of bounds, then it's going to die horribly, hopefully. Let's see. So I'm going to recompile it. I'm going to copy it back to the other machine, and then I'm going to try running it. Yay, look, and we get through the first 5 values, which are in the allocated part of memory. And then as soon as we get past that, we get a trap in address space security exception. Now, what I'm going to do is I'm just going to run this on this machine here, which isn't a capability machine. That's just a common or garden Intel machine, I think. So if I compile it on here, gcc foo.c, and then run it, oh, look. So on my Intel machine, I can go out of bounds. Oh, how sad. Whereas on my nice capability machine, of course, I can't. As soon as you trespass one word over your limit, then you get this violation, which traps. So in fact, you get a signal. This is a new signal called sigprot, which is a capability error, and you can handle that. But because I didn't have a handle registered for it, then I just aborted execution of my process. So you might say, well, that's just like a seg fault, really. But the point is, this is so fine-grained here. Instead of protections at the level of pages, now we have protection at the levels of individual allocations of memory. So this is very fine-grained memory protection. Okay, so this is possibly the slightly ambitious part of the talk. Build your own malloc before lunch. So let's see if we can make our own memory allocator. James, a question, please. Yes.
Can you instrument C compiler to issue warnings that you might be about to?
Oh yeah, okay. So good. Can you generate warnings in your compiler that there might be capability violations?
I mean, for foo, it's statically observed.
Yeah, definitely. Yeah, okay. So there are sort of static range checking algorithms that you could employ. I don't think they're built into the default CHERI LLVM compiler, but you can imagine incorporating those kind of things. There are some warnings. So when you try to do dodgy things, casting pointers to integers and so on, the LLVM compiler that we're using here will warn you about that. It will say you're losing capability metadata. So it warns you about unsafe operations in terms of typecasts, but I don't think it will warn you about unsafe dereferences based on indices of arrays and so on. Thanks. Build your own malloc. Okay, so let's become software engineers for the next half an hour. So we want to reserve a big buffer of memory. We want to mmap ourselves some memory, and then we want to sort of allocate small chunks of that big buffer as clients request to malloc small units of memory. And once we've allocated the chunk, then we want to make sure that we don't give it away to somebody else at the same time, unless it's first been freed by the original client. Okay, so the only change to our requirements in our CHERI world is that we want to return bounded capabilities rather than arbitrary pointers. A bit like you saw when I did malloc there, as soon as I went out of bounds, I got the error, and that was because the bound was encoded in the capability which was returned by malloc. Okay, so I'm actually going to try and go quickly through two very simple allocation algorithms, and the first one is a bump pointer allocator. So we've mapped ourselves a large contiguous region of memory, okay, which is this yellow block here. And before we allocate anything, our sort of next word to allocate pointer, the green pointer, is pointing at the start of the block. And then I say malloc me some memory. Okay, so this red portion of memory is now in use by the client. Okay, so I return a pointer to this memory to my client, and they can then use this. Okay, and I make sure that pointer is bounded, so they can't go past the end of it before the beginning of it. And then my sort of allocator internal variable that tells me where to allocate next is shifted along. I've bumped the pointer. And then I do the same again the next time I allocate some memory and so on. Okay, so let's see what that looks like in source code. Okay, so I've just got to initialize the allocator, which is just going to mmap me some memory that I can then use. And I say how much memory I want to have in this large block. And then every time a client wants some memory, it just calls bump alloc. This is my malloc effectively. And free becomes a no-op because once I've moved the bump pointer on, I never want to move it back because I'll have holes and I might not be able to satisfy the space requirements and so on. So I do get some sort of internal fragmentation here, but don't worry about that too much for now. So I've got my allocation buffer and I initialize it with an mmap. Okay, and I say how much memory I want, and let's just get rid of that. The protections. So possibly I want props exec as well if I want to execute memory, but let's not worry about too much for now. This is anonymous, so it's not actually a link to any particular file or address or anything. And I return that. Sorry, I store that mmap buffer into my buffer pointer. And then when somebody wants to allocate some memory, which is len bytes long, then I just want to, well, what I really want to do is add my amount of memory I want to allocate to the buffer, and then update the big green arrow, and then return the original green arrow pointer, which is now my sort of user visible allocated memory. But the problem is we have all these extra CHERI things here. So this code here, so to use CHERI API calls, you need to include this header here, CHERI in trin, which gives you all the compiler intrinsics for CHERI. And if you're using the CHERI LLVM compiler, then this is just on the standard include path. Okay, and then what I need to do is to make sure that the memory I allocate is representable in this compressed CHERI format. So remember I said you really need 256 bits to store a full fat pointer. Well, actually, the architectural instantiations of CHERI compress that down to 128 bits by sharing some bits between the base and the offset and the bound of the pointer. So you sort of effectively do a kind of lossy compression on the fields in your capability. But what that means is you can't represent all capability sizes and all capability values exactly. So you need to sort of possibly pad your capability to make it a bit bigger to satisfy the client requirements and satisfy the CHERI representability requirements. That's what all this code does here. And then once we've got a chunk of memory that is going to be a capability of an appropriate size, then we set the bounds, and we set the bounds to the length that our client has requested, possibly rounded up to the nearest representable length. So for anything that's smaller than a page size, 4K, everything's exactly representable. It's only as you get larger that some of the capabilities are needing to be padded. A question? Yes, please.
There's here the restriction on the bounds.
Yes. Ah, good. Okay. So if I wanted to restrict the permissions, I could do that as well. So yeah. Okay. So I don't think this is executable actually, because I think when I did my mmap call, where's it gone? When I did my mmap call, I only specified this should be readable and writable. So that means any pointer derived from this pointer here will have the same permissions, readable and writable. When the mmap returns, its bounds are to the nearest page, and then they get restricted by the client code. So let's put in some debugging printf. Should we do that? Is that a good idea? Well, let's do it anyway. Let's see. So if I say printf, so large buffer is at, now if I use that format specifier, then I think that will give me the capability permissions. Okay, and then if I do the same for my client alloc, that will give me the permissions there. Here perhaps. Okay, so yes, there are also C API calls to set the permissions as well as the bounds, and so we could have restricted those perhaps, but I don't do that here. I'm assuming I want them to be RW. Okay, right, so do we have a client here? Good client.c. What does this actually do? Allocate some memory, does some storing of values. Let's try and compile it and see what happens. Good client.c, and I also want bump alloc.c if that can work. Oh dear. Where's that? Oh, maybe it isn't. Dot, is it? No. Dot slash dot. Ah, good. Okay, right. So hopefully I've got an executable now. Yes, so I'm going to copy that over to my machine and try and run it. That's still open. Oh, the other thing to say is these machines are remarkably stable. Look, this one's been running for a month and hasn't fallen over yet, which is very respectable for research operating systems and research hardware. Let's run the program. Ooh, right, okay, so let's see what happens here. Help. Lots and lots of debugging output. Did I ask for all this? I must have done, mustn't I? I think that's a good idea. Good. So it's only the first few lines I wanted, really. So there's my large buffer, which is the result of mmap. Okay, and we see this is 1 page long. Okay, so those 3 zeros there indicate a page boundary, a 4K page boundary. And then I've got permissions to read and write values into there and to read and write capabilities into there as well. That's what the capital R and W mean. Okay, and then my allocation here, my initial allocation is only allocating 4 bytes. Okay, so look, the bounds here are just the 4 bytes rather than the full 4K there. And then there's another one, and so on and so on. And we see it going all the way down. And then we've got, yes, this is what the debug printf gives me in terms of the different metadata for the capabilities. Okay, so that's a very simple bump pointer allocator. And what we see there is that the 2 changes we had to make were, number 1, to ensure that our capability was representing a value that was appropriate. So in our compressed CHERI capabilities, not all bounds and base and limits are representable, so we need to make sure we can represent what we want. And then secondly, to enforce this restrictive range for the client capability. Okay, so this is the CHERI concentrate here. When they did some experiments, the folks at Cambridge, they found that using 256 bits for the capabilities just hammered the hardware. Basically, the data bus width was too big, and the cache was too bloated, and so they compressed things down to 128 bits, which is kind of double pointer size, and found that this was a fair enough trade-off. So effectively, it's a bit like a lossy compression here, where your base and bounds and offsets somehow share some bits, and then you shifting and masking to make sure you get to the base and bounds and offset correctly. So perhaps there's a bit more complexity in the encoding and decoding of capabilities in the hardware and in our software as well, but it's much more space efficient. Okay. So the second, questions, please. Hello. Where are you pointing? Over there, sorry, I beg your pardon. Yes, hello, shout it out. Oh, it's an indirection. Great, excellent, good. A valid indirection. Yes, hello.
So your error message. Sorry, both my comes at once.
Yes, yes, this is all checking at runtime. Everything's enforced dynamically.
So if you look into typing assembly,
typed assembly language. Yes.
You could imagine a piece of hardware that just implements the service of some kind and then has to go into the machine and type to and say upfront this is not going to work.
Yeah, so in this system, everything happens just in time, dynamically. Yeah, but what you're suggesting is that you could somehow have a more sophisticated. Yeah, sorry, I'm just trying to understand. Yeah, a more sort of sophisticated instruction decode or interpretation mechanism that would perhaps identify problems before we got them into the kind of execution pipeline. Yeah. Yeah. So yes, good. So can we analyze this to identify problems ahead of time? And I think that's similar to what James was saying before about even the compiler trying to do some sort of data flow analysis to understand whether there are problems. And those things are possible, certainly. So in the case where we are good citizens and we're just trying to write bug-free code, okay, then that would work nicely. But if there are evil actors out there who are trying to compromise our code base, then they will be trying to inject code into our system somehow that they know is incorrect and is doing the wrong thing, and they want to try and circumvent any kind of checking mechanisms. So they don't care about compiler warnings or error messages. They want the thing to do the malicious kind of harmful operation.
So at most times,
to avoid problems with those kinds of memory-induced bugs. Yes, I think so. Yes. Thank you. Good. Hello.
So I think earlier you said that any time any program modifies a bit pattern of a pointer, the tag bit gets set to 0, right?
Right. So sorry, if you modify the capability metadata or the base or the limits in a way that somehow fails to respect the monotonicity properties of capabilities, then the tag bit gets invalidated. But it is possible to do pointer arithmetic on capabilities, say.
And is that for like any instructions? Or is it specifically for, I mean, also, I guess the other half of the question is, what are the CHERI intrinsics? What do they look like? Oh
yeah, okay, good. Okay, so let's see if we can find the CHERI intrinsics. They do map down to assembler instructions, but they're all, oh dear, I wonder if I've got this here. They're all, now it's going to be one of these, maybe that one. Bingo, look, CHERI, C and C++ programming guide. So they're all mapped onto kind of C calls here. So these are just extracting the appropriate fields from the capability. Okay. But then you can also set the address. Okay. And you can set an out of bounds address. Okay. And then you can set the bounds. Okay. But if you were to increase the bounds rather than narrow them, then your validity bit gets, your tag gets cleared. Yeah, okay. And then here's the permissions changing as well.
But do these functions wrap like regular ARM64?
Yes. So they're not regular ARM instructions, they're new instructions for this capability architecture. Oh. So there is a new, here we go, a new architecture specification ARM have released that has extra, let me go back to the top here, that has extra instructions to manipulate capability values. So look, here we go. This is the Morello, that's the name of the code name of their capability system, the Morello instruction set supplement, and let's see if we can find the extra instructions down here. Oh, here we go, here's instructions here. Which ones do we want for capabilities? Oh yeah, here we go, new instructions. So let's see if we could find one of these. What does this one do here, for instance? There we go. So that one is mapping onto the permissions bit that we were looking at before. Yeah. Okay, so these are new instructions, but only supported on this AArch64 variant architecture. So ARM say A64 is their sort of default ARM, and they say C64, which seems a bit retro to me, doesn't it? C64 is their capability-aware 64-bit architecture. So if someone says, I've just got a C64, they haven't sort of gone back in time for the 1980s. They're using new ARM Morello instructions. Okay, thanks. Were there any more questions? Oh, yes, thank you. Oh.
When exactly the checks happen?
The overhead, did you say?
Yes.
Yes, good. Okay, so you would imagine that all this checking would be very expensive. Well, there's a lot of expense, right? Because there's the expense of all our pointers being twice as wide as they were before. There's the expense of maintaining all these tag bits in memory. And then there's, as you say, all the dynamic checking on every pointer access. Yes, okay. So where I'm going to get to, hopefully by the end of the talk, is trying to convince you that capabilities make the world more secure and possibly more performant. But at the moment, you might find it quite hard to believe that. At the moment, you think we might be trading off some performance in order to get a higher level of security. And maybe that's acceptable. So really, the whole motivation for ARM implementing this Morello capability architectures to try and understand these trade-offs and see whether this is a machine that, you know, runs like a dog, or is actually a high performance, viable alternative mainstream architecture. Yeah.
So as far as I understand, we know much more with them, but more like our architectures, all the checks are still present. Like when the segmentation of painting and so forth, checks are still present. So
Yes, yes. So a standard architecture would have a memory management unit that would enforce page level checking. Yes.
So does this replace noise checking, or it's on top of that?
It's on top of that.
Also?
Yes. Yeah.
And how does this do with caching?
Yeah. So the caches have been re-architected to support this as well. Yeah, that's right. So there's extra bits in the caches and in the cache logic and so on to support this too. So it is a real bottom-up redesign of the architecture in some sense. Yeah, yeah, that's right. Yeah, so we haven't thrown away the page level memory protections. They're still there as well. Yeah, this is kind of on top of that. Yeah, thanks. Okay. Oh, we have so many questions. Hello, yes.
You mentioned performance costs.
Performance costs, yes. Right, so that's clever. So can we kind of parallelize these and run them sort of side by side? Yeah, yeah, yeah. Yeah, so some of the things can be run side by side, and in that case, you're not so much paying in terms of time, you're paying in terms of silicon, because you're spending transistors on this that otherwise you could have used to make your cache bigger, or your support more operations in your ALU or something like that. Yeah, okay, thanks, that's a good point. Yeah, good. Hello.
I was basically thinking that in order to make best use of this, it really needs to be verification.
Ah, verification, the B word. Excellent, good, well done. Yes, 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 that's nice, good. So after all, this is the SPLV summer school. Yes, we should talk about verification. So I am not a verifier, that's not right. I'm not a verification person, but there are lots of people who do formal verification, including Peter Sewell's group in Cambridge, for instance, and also some folks at Edinburgh. I think Brian and his gang at Edinburgh do verifications as well. And in fact, Rekha and Simon are here, and they're from Oxford, and they're using the ARM Morello system, and they're possibly going to be using separation logic, is that right? To do some kind of verification of memory allocators, including some of the allocators that I'm going to show you a little bit later, hopefully. So there is a big verification effort going on to make sure that these things are doing what it says on the tin. Does that address your concern? Yes. Thanks, thanks. That's good. Yeah. Okay, great. Very nice. So, oh help, it's nearly past. Oh dear. So I'll tell you what, I'll just whisk through this really quickly, right? So you've got a big block of memory. You've M-mapped a big block, okay? And now you're splitting this up into small chunks of memory ahead of time of pre-specified sizes. Okay, so all these chunks are the same size, and then you just sort of build up a linked list. Okay, so you put a pointer into the next one along. Lots of memory allocators work like this, and one interesting side effect is now every block has to be at least large enough to store 128 bits for a pointer, so you can have the linked list in here. Then when somebody asks for some memory, your green pointer points to the first free block, okay, and then you allocate that to the client and return the pointer, and then you chase the tail, and then there's the next free block in your linked list. And you'll have several of these linked lists of different sizes, okay? And you will have different size classes, and then when somebody requests memory, you look to see the largest, sorry, the smaller size class that's larger than the memory they're requesting, and then you return that. I'm not going to show you the source because we've got time. So I want to tell you very quickly about the implications that CHERI has on allocator design, memory allocator design. Okay, so you know, every time you malloc some memory, there is metadata associated with that. You know, if you use, say, Doug Lee's malloc, which used to be a very popular memory allocator, every time you call malloc, right, for a particular size, and you get back your memory. If you look one word before the memory you allocated, inside there is the metadata that tells you how large that block is. That's interesting, isn't it? So actually, you've always got an overhead, a payload of one word of metadata with every block that you allocate with dlmalloc. Okay. But if you're bounding capabilities to be bound to just the limits of the user visible portion of the buffer that you allocated, then you can't see that metadata anymore. Oops. So you need to sort of keep a higher privilege capability somewhere that allow you to get back that metadata. Okay, coalescing is very tricky. So I don't have a picture for this, do I? If you've nmapped a block and then you nmap another block and they're contiguous, they're next to each other in memory, you might just want to treat them as one big block, especially if you're trying to balance something that would only fit in both of them rather than just one of them. Okay, but nmap returns you capability here that's bounded there, and then another capability here that's bounded there. And even if you have two contiguous capabilities, but with non-overlapping bounds, you can't access that capability, you can't access memory and that capability with that, and all vice versa. So coalescing blocks becomes much more difficult. You can't sort of munge things together very easily unless, hello.
Is there capability scope to block both blocks?
So you're talking about reserving portions of the address space, perhaps? No?
You know, like scoping in like C or like blocks of code. So,
Oh, right.
so
I see.
it seems like something that might make sense where when you need to scope, you use the capability.
Right, okay. So this is like RAII or something like that in C++, perhaps. You're thinking about a kind of dynamic nesting, or perhaps like arenas or regions or something like that in memory management. Yeah, okay. Possibly, I should have to think about that. Let's talk about it over our sandwiches. Yes, thank you. That's nice. Good. Coalescing is a problem unless you have a super capability which allows you to access the whole of this memory here. So that's a challenge. Imprecise bounds, as we saw, added lots of lines of code to our allocator. And then temporal safety, this idea of revoking, sweeping memory to revoke pointers that have previously been freed, is also a challenge. So here are 4 real-world allocators. These are memory allocator libraries which have been ported to CHERI. And what we see is these are lines of code different here. In some cases, you're changing less than 1% of the lines of code. In the worst case, maybe the best case, you're changing, there you go, 5%, 6% of the lines of code. Now, if you read all the sort of shiny, glossy publicity material from Capabilities Limited, which is the spin-out company for CHERI and capabilities, right? They say, on average, you'll need to change, and they did this over a lot of open source code bases, you'll need to change 0.02% of your lines of code, which isn't very many, really, you think about it. Of course, you probably have to look at more than that, but you only have to change that many, they say, 0.02%. So I assert confidently here, you need to change at least 1 order of magnitude more than the average for a memory allocator, possibly 2 orders of magnitude in some cases. So memory allocators definitely need severe re-engineering for CHERI. We started looking at the BOEM garbage collector, which is a C and C++ conservative garbage collector, and we've been porting this to CHERI. I'm really motoring here because of the time, sorry folks. And we found one nice thing. So because you've got tags in your memory to indicate where pointers are, suddenly a C++ conservative collector becomes precise because you know exactly what the pointer is. You've got this kind of type level information stored directly in your memory, which is very nice. But there are complications, as we saw before, in terms of coalescing and metadata storage and so on. Read our paper if you are interested. These were the challenges we found. BOEM, as most low-level C systems code from the 1970s and 80s, assumes that words and pointers are equivalent and can be cast between. the problems of bound precision as well, and coalescing. But this is the point I was trying to emphasize before, as well as challenges in terms of porting legacy memory allocator code to capability platforms. There are also opportunities in terms of improved precision with the hardware tags, in terms of using CHERI protections instead of things like munmap to reduce availability of memory regions to clients and so on. So maybe these opportunities mean that hardware support will allow us to do certain kind of memory protection more efficiently. So this is the vision. This is what we really want, of course. We want memory allocators and systems that are more secure and at the same time have higher performance. Will they? Do they? Well, watch this space. So what's happening at the moment is a lot of people are building code for these ARM Morello platforms and benchmarking them to see whether we do get improved performance as well as better security. And that's what we're doing right now. I was asked whether, I'm just going to say this and I'll answer your question, I promise. I was asked whether you wanted a practical lab. I think we ran out of time, didn't have time for a practical lab, but I'm going to suggest some practical steps that you can take if all this stuff has whet your appetite for more secure C programming. That's it, maybe. Well, here's 4 things you can do. So the first thing is go to GitHub and look for the CHERI build project. That's from the Custard team at Cambridge. It's basically just a Python script that you run that then downloads lots of Git repositories, builds a QEMU instance that allows you to run CHERI code for RISC-V or ARM, builds the modified Clang toolchain and the CHERI BSD operating system. You'll have to leave your computer churning away for hours, if not days. But eventually you'll end up with an emulator that can emulate CHERI programs quite quickly. Oh, I will stop and take a question there. We better do this in order, haven't we? Go on. Question, yes, go.
So, right, alternatives. I know there's some security that put a name for it that intercepts every single port of the operating system.
Ah.
Interceptors, and it's kind of like an active firewall you're working on.
Yes, okay. So even SE Linux can do some things like that, can't it? Yes.
Yeah.
So other security mechanisms and how they compare and contrast with this one here, you're saying? Yeah, okay. So I think I'm not a cybersecurity wizard. I think there are different trade-offs here, and you'll need to work out what you need to deploy to harden your system sufficiently for the kind of threat model that you're anticipating. Sound of buzzwords, I hope so. Yeah, so I think it could be that you used those kinds of operating system level protection mechanisms or checking mechanisms as well as these things, and they were perhaps orthogonal. Possibly. So certainly dynamic instrumentation tools can rewrite programs on the fly and kind of in a kind of just-in-time way intercept certain instructions, say, and rewrite. Yeah. Yes. No, I wouldn't say CHERI was unique, but I'd say it's probably the best of the bunch in terms of tool chain support, and also in terms of real hardware that does stuff. So you can get FPGAs that will do some of these things for you, but they won't boot a full Unix operating system or have a standards compliant C compiler. Yeah. Okay, thanks. That's good. Oh, more questions. Who is next, please? I don't know. Yes. Hello. Yes.
It's all about security.
It's all about security, but also about performance, possibly, yes. Okay, so the problem is, right? Yeah. Yes, okay. And the most hilarious thing is when you run the Python script and it loads CHERI BSD for you, you get a root user with no password. That's highly secure, isn't it? Yeah, but it's all just in your QEMU instance. That's okay. Yeah. Yes. Sorry. So yes, that's just a kind of experimental approach, just to try the thing out for yourself. Try before you buy. Yes, yes. So thanks. I appreciate your comment, though possibly might be yes, slightly facetious. So that's okay.
Like, if I was wearing a tinfoil hat, would you want to?
You wouldn't run a Python script that runs for days. No, okay. So in that case, what you can do is you can download each Git repository individually and look at the code and then run make world or whatever for every one of them. But there's probably there's the CHERI BSD operating system, there's a Clang compiler, there's QEMU, so that's at least 3, and then you probably need a couple more repositories as well. This is like a sort of meta repository manager thing that lets people who are less suspicious than yourself build the CHERI world in you know, one command. So thank you. I see where you're coming from there. Yeah, thanks. Hello.
I mean, so you keep running into these coalescing buffers.
I do have problems with coalescing. Yes, I do.
You have 2 points. Yeah, you use them as kind of proof. You know, I have this. Just give me a new one.
I know, but the problem is it doesn't respect the monotonicity property that's been formally verified by, you know, Peter Sewell et al. So yes, it's yes, good. Okay, so could you somehow sort of offer up your 2 capabilities to the operating system and say, please give me a capability that spans both these, you know, contiguous regions? Yes, and I have spoken to people about that, but so far they haven't been forthcoming. Yes. Okay, I'm going to try and finish this really, really quickly. So once you've made the CHERI world with this CHERI build thing, you could try some simple CHERI coding examples, a bit like the ones I demonstrated here. So there's the adversarial CHERI examples, there's the CHERI examples from the capable VMs. That's me, I'm capable VMs, or part of the capable VMs project. So Google CHERI examples, capable VMs, and you see lots of lovely memory allocators which you can play with. Or you could read my, it's only just started, online book. It soon will be an online book. At the moment, it's an online frequently asked questions list, about 3 questions in it, but it's going to grow. Capabilitiesforcoders.com. And if you really think this is very exciting, you should go to dsbd.tech and fill in the online web form and ask them to send you a Morello system. And they will. It'll come via DHL in 3 days. How exciting, if they've still got it left, whether they have or not. But yes, that's, you know, very exciting indeed to think that there's real hardware out there and taxpayer money's gone into sending you a Morello system. Good. Okay, that's the end of my slide, so I shall take further questions. Hello. Oh, yes. Yes.
What's the relationship between weak memory behavior
yes.
and capabilities?
Yes.
Well, do they match that?
So this is an ARM system, so it has a kind of ARM memory model, yes. And I think everything I've showed you here has been in the context of effectively single-threaded code. And once you start thinking about a more concurrent system with lots of things happening, then yes, there will be an interplay between weak memory models and capabilities. That's beyond the scope of my slide, but it's certainly an interesting area to think about. Thank you. That's a nice connection between Wednesday's talk and yeah, thanks. Hello.
So, you know, like to modify these pointers, you need these special instructions.
Yes, special instructions are required to modify capabilities. Yeah.
Right. So, but you know, if we were to take a regular compiler, maybe it tries to be smart about, oh, I saw that you had previously allocated ints, but actually puts in one of these stat pointers. Maybe like I try to reuse that state. Do you ever find any problems with like the compiler optimization causing kind of false flags or false positives in terms of the query?
Yes. So when we compile our fork of the Bohm garbage collector, at the moment we're getting 120 compiler warnings, and I think the majority of those are false positives. Yeah. So you can do, and there might be some refinement in terms of the compiler warning messages.
Have you seen a compiler optimization cause a crash? A runtime crash?
Ah, that's good. Okay. So not personally, but anecdotally, I think there has been some evidence of that. Yeah. Okay. So I think inside LLVM, maybe some compiler optimizations aren't turned on for capability backends, perhaps. Yeah, thanks. Questions stand between us and lunch, but go on.
So, is there any protection against like random
Good, cosmic rays. Yes, what happens when a cosmic ray zaps your capabilities? So I think you can still have ECC, error checks in your RAM and so on in capabilities. So there are those kind of mechanisms that would perhaps be available, but yeah, if a cosmic ray zaps your permissions bits in your capabilities, then I'm afraid all bets are off. Yeah, that's true. I know.
All right, let's ponder this over lunch. Thank you very much. Finishes the official lecture program for the summer school, and let's actually also have one secret